Good afternoon, everyone. My name is Mohammed Wabi. I'm a senior design engineer working in the trackbed investigation team. This is my colleague Leventi Noggi, Ulring Leventi Noggi, is it? Leventi Noggi, who works also as a senior design engineer in the trackbed investigation team. Now, today I'll be talking to you about the research that we've been carrying out for the last 12 months about geocells. It's basically our baby, me and Leventi. We were obsessed with this product. We've been working on it for some time now, and we're here to tell you some new stuff that we found out. Just to let you know, I know I've gave a couple of presentations in the past about geocells. I promise you, it's new stuff, so don't get bored. Just okay. Now, the outline of the presentation will go as following. We'll just go through very briefly the background, the old stuff, the boring stuff. And then we'll talk about the aim of this research that we've been carrying out, and then we'll discuss and show some results that we obtained from laboratory testing and numerical modeling. And that's basically all me. That's the boring stuff, theoretical. And then Mr. Noggi is going to come down and basically steal the show and with his impressive stuff about installation. So it's a mixture between theory and installation guidance. Now, what is geocells? Geocells are basically honeycomb panels. They look like a geogrid, but they're extruded in the vertical direction. It's not a geogrid, but it looks similar. You fill materials inside, and basically it creates a reinforcing effect on the subgrade. It has been developed by the US Army to build roads for jet fighters and tanks, so it's quite robust, and it can reduce the depth of construction by almost 40 to 50%, and it's very cheap. It costs about £6 per meter square, so it doesn't cost very much, and it can lead, if it's applied properly, it can lead to a trackbed, to reduce the cost of the trackbed installation by about 20%. But that's basically applying it carefully. Now, how does the geocell works? Now, the geocell works in three mechanisms, in three ways. So it creates a vertical confinement, and that vertical confinement is due to the friction of the geocell, internal friction of the geocell wall. It also creates a lateral confinement by developing something called hoop stresses. So you apply the vertical pressures, and then you get some hoop stresses that confines the material in, doesn't allow it to move or deform laterally. And then if you've got excessive loads, you can end up with a tension membrane effect. So you get some tensile strength out of that. So this is how it generally works. Now, it all sounds good. There's about tons of research that actually proves that it works, but there's a problem. Well, designers and contractors are reluctant to use it. The designers are reluctant to design for it because there's no universal way of designing trackbed with geocells. That's a struggle. I'm a designer myself, and it's not an easy task to do. There's many ways, but there's no universally agreed way. And also, there's a limited experience with installing geocells. Yes, we have seen sites since probably early 90s, maybe 80s, that had geocells, but you know, it's still limited. It's very done for bespoke sites. Now, so what's the aim of this research that we started? The aim of this research was to basically come up with a comprehensive guide that provides designers with design guidance and best practices for contractors to carry out the installation in the most efficient way. But how can we do that? Well, in the TBI, we're mostly a design team, really. So we had to have some sort of a collaboration. So we worked with IP Engineering and Innovation and the TU Klauser University in Germany, which is a leading university in geocells research, on trying to understand how we can design and install geocells in the best way possible. Now, to go through the lab testing, well, TU Klauser University proposed this kind of test configuration where we basically relied on applying a plate load test for a trackbed with different geocell thicknesses, reinforced and unreinforced, and it was instrumented with a number of pressure sensors, settlement sensors, and so on and so forth. And we have been doing the tests for a number of different soil stiffnesses. So the tests are currently ongoing at the moment. So we're still getting the results. There's so much data coming through now, and we're still in the process of analyzing them. But I'm just going to go briefly with some of the most interesting stuff that we so far have managed to understand. So, as I said earlier, they've instrumented the rig with different pressure sensors. So what we've done, for example, we applied a plate load test on different tracks with different sub-ballast or fill material thicknesses, reinforced and unreinforced. And so we've got 150, 200 mil, and 300 mil. And this is the amount of stress being felt by the subgrade. So you can see how much the stress being exerted. And this is the most important thing for us, because if you know the stress, you can know how much the subgrade is going to settle. You know what sort of failures that you may experience, as Matt has explained in his previous presentation. So it's very important to understand that. So from the geocels, for example, for the reinforced case or unreinforced case for the 150, you can see we're getting about 30 kilopascal if we apply 250 kPa on the surface. If you put a geocell, you reduce that by 33%. But if you go for a 200 mil geocell, you reduce that by 20%. But if you go for 300 mil, the impact is very minimum. And that's confusing. People will think, hang on, if I have thicker geocell, it should work better. Well, yes, true, but geocells only work if you get lots of stress being applied. But because there's so much stress being dissipated by the time it reaches the subgrade, the impact is very small. So therefore, you're seeing this sort of impact. If we had higher stresses being applied, it will basically get the geocell kick in for these particular cases. These are the results basically for the plate test. So what you see here, the same thing, 150, 200, and 300 mil of ballast, reinforced, unreinforced, and this is the plate test results. So they're measuring, this is how much stress being applied or pressure being applied on the surface, and this is basically the measured settlement at the surface. And you can see they apply a load up to 8 increments, up to 500 kilopascal, and then they remove the load and then reload again, and so on and so forth. So they're doing it for reinforced and unreinforced situations. And you can see it's very clear here. This is the reinforced case and this is the unreinforced case. The difference between them is quite massive in terms of settlement and deformations. The same thing you'll see here on the 200 mil sub-ballast as well. You can see the differences are quite prominent. Just be careful when you're looking at these graphs. The y-axis here have different scales between one case to another. But we start here with a difference of 24 mil in terms of settlement, and then we go to almost 8 mil here, and then we go to a difference of 2 mil in terms of settlement. So this is all nice. So what can we do about it? Well, we are trying to extract as much information as engineering parameters from these tests, because there are different ways of interpolating these results. And we basically took the information from some of these tests and we plugged into our finite element model. It's not as fancy as what David has shown you earlier this morning with his modeling stuff, but it should do the trick for us. So we've used a 3-dimensional finite element dynamic model. So it's a moving train. So we've got a Virgin Pendolino train here that is moving on this sort of embankment, and it has a total depth of almost 50 meters. So it's quite thick in terms of the analysis, and it's running at approximately 100 miles an hour. And we looked at 3 design scenarios. So this is what are the design scenarios. So we're looking at standard design right from our design standards. So exactly, this is the standard. If we've got this kind of soil, we're going to have this sort of design. And we're looking at 2 alternative geocells with reduced thicknesses. Okay, and the soil that we wanted to look at here in this case is about 20 MPa. So it's somewhere towards between firm and soft clay. And we're looking at a line speed of 100 miles an hour and quite a high traffic, 30 mGTP. And we've carried the analysis for 30 years. So the purpose of this analysis is put the parameters from the test in the model, try different designs, and look at the total track settlement, because that will basically drive your maintenance, tamping, and interventions. And obviously, for the purpose of this exercise, we assumed no tamping or maintenance is taking place for 10 years. So we just want to look at the raw total track settlement and see what we get out of it. Okay, for those 3 cases, we looked at the standard design by Network Rail standards is 300 mil ballast with 250 mil fill material. We proposed an alternative with the same thickness but with the reinforced case, and with a reduced depth of 150 mil fill. So basically consider 3 cases, and we wanted to look at the total amount of settlement across the subgrid for the model. Just to bear in mind, the model has a length of 59 meters, so we're looking at 59 meters, and it has something a bit unique you wouldn't find in a lot of models. It has inherent track geometry, so we wanted to generate dynamic loading, okay? If you run this model with smooth surface, probably rail surface, you're not going to get any fluctuation in dynamic modeling, no significant fluctuations in dynamic modeling. So what we've done, we basically created some sort of an inherent geometry on the surface of the rail just to generate these sort of dynamic loads, to be as realistic as we can with the modeling. And this is the results. Basically, the results, this is the track settlement along the track for after 10 years, the total track settlement. So we're talking about ballast settlement plus subgrade settlement, okay? And you can see here, the green line represents the case where we had 250 mil fill with geocells, and the blue line, which I'm not sure is very visible, represents the 250 unreinforced, so like for like in this case. And you can see that the one with the geocell seems to be settling at a rate about 20% less than the unreinforced case from the settlement point of view. But if you reduce the geocell thickness to 150, you seem to almost end up with a very close answer to the unreinforced case with 250 mil thickness. So that basically tells me that if I replace my standard design with a reduced standard design by 40%, I'll probably end up with the same performance for that particular case. Now, things can be different for different ground conditions, different stiffnesses and so on, so that cannot be applied everywhere. But for the sake of this exercise, this seems to be the case. Now, to validate this, or not to validate this, but to see if this is what we're getting in the practice. Well, a year ago, 2 years ago, we worked with David Woods on the Northern program, where we basically installed geocells, or designed geocells with reduced thicknesses. And for that particular track that we looked at, the standard design had 230 granular fill and then 50 mil of sand. What we did with the geocell, we reduced the 230 to 150 mil with the geocells. And then we installed it. Now, things were all right, and we started monitoring it for the last couple years. And this is where we installed the geocells, basically. This is where the geocell installation took place, and you can see the track quality here on the y-axis, and this is basically time. The last recorded geocell installation or renewal was done in 2002. Now, if you want to compare the performance after the geocell installation to a performance, it has to be compared to the last recorded major renewal. And you can see there's a significant change in the rate of deterioration in track quality just by installing the geocell, even though it has basically a reduced required thickness, but it seems to be performing in a very stable manner. And you can see, so if you look at the rate of degradation of track geometry, at the top 35, it used to be degrading at 0.15 mil a year. Now it's almost not deteriorating at all. Sorry, it was deteriorating at 0.7 and then reduced to 1.5 mil a year. On the top, we're seeing something similar. It used to be deteriorating at 0.9 and now it's deteriorating at 0.1 mil a year. So it seems to be there's a massive improvement in terms of performance after the installation of geocells. Now, what's the beauty of this? Well, the beauty of this, it was 20% cheaper than going for the full dig. So we managed to reduce the dig depth and having a very good performance. And I think the estimated saving was about £300 per meter, linear meter of track installation. So it seems to be quite impressive. Now, I'm going to hand over to my colleague, Levente, who's going to go through all the practical aspects of installing geocells properly. Thank you.
And the middle is the pointer. Yes. Okay. If there is something that's not up for debate from Mohammed's presentation is the fact that I'm Levente Nagy and I'm a senior design engineer in Network Rail. So basically, we started installing geocells on isolated sites since the 80s. But because that was just a small number of sites throughout a few decades, technically, the installation contractor didn't get to learn too much from their mistakes because they never repeated, they never had the chance to repeat such an installation. But nowadays, because we understand better the benefits of the geocells, we are installing and specifying more and more such products on our sites. And obviously, like any novel product or any new installation process, that comes with the inherent mistakes that we are trying to learn from. So we are continuously gathering the feedback from our installation contractors, and what we are working on is to put together a guidance that will be useful for the whole rail industry in the future. So I'll start listing quickly the main stages of the geocell installation. The first one is preparing the subgrade, compacting it, installing a geotextile, expanding partially the geocell on top of the geotextile, connecting two consecuting to abutting panels of geocells, and that's followed by the full extension of the geocells using various methods: T-bars, ATRA anchors, wooden stakes, infilling selected cells on the ends of the panels, or something that we, I could say, invented in IP track. Our contractors came up with this idea of using some steel bars that keep the geocell panels extended. Next one is unloading the granular infill. The other one is spreading the infill, and finally compacting it. So I will give you a little bit of details from each of those stages. The first one is subgrade preparation. Now, on most of the sites, that's not necessary, especially on track renewal sites where we are putting a new track on in the place of the existing one. So it's just simply digging it out. That's enough. But in some instances where we have virgin ground or some excessively poor subgrade like this one, we need to do something about it. So that's probably the best example. That's on the Filton 4 tracking enhancement project. As you can see, that was a waterlogged subgrade, a lot of moisture, very soft material that had to be dug out. That was replaced with type 1, a type 1 layer placed on a geotextile. Eventually, the geocells were installed on that type 1. And at the end, the sand was used as a granular infill, and it was compacted. About the expanding of the geocell panels, as I said, there are various conventional methods that have been used, and they are still being recommended by the geocell manufacturers. But our colleagues in the contractors' teams and from IP track, they raised some safety concerns related to the continuous hammering of some stakes or bars. You can imagine we are supposed to install tens and hundreds of those on a single site, so that may be a valid concern. And eventually they proposed this kind of arrangement. These are steel bars, and they are keeping the geocell panels expanded. Okay, the next step is connecting to abutting panels of geocells. This is very important. Otherwise, if we are not connecting them, we are not achieving a continuous stiffness of the layer, and there is a risk of differential settlements. Now, to aid the installation of the panels, it is very helpful to connect as many panels as possible beforehand on the side of the track. So bear in mind, the panels are coming from the manufacturer in 5-meter length. So we are trying to connect up to 40, 50 meters, and they are easily expanded on site. And obviously, even these 40, 50-meter sections need to be connected between them. Also, just something that I should mention, once they are connected and before coming with the granular infill, these geocells are an obstruction for walking and for movement of plants. So we need to make sure that on the CES we have a clean and safe walking route for our personnel. Unloading the granular fill, conventionally that has been done with dumper tracks. It can be done with excavators taking the infill material directly from the adjacent track, from the wagons. or something that our very clever colleagues from IP Track, they used an MFS machine. So that conveyor belt can very easily and very quickly unload the sand. Now, obviously, on the single line working, that there could be a little bit of problem because you only have this limited room for expanding the geocells. Now, that means that you have to spend a lot of time connecting short sections of geocell panels. Now, that can be overcome by preparing a longer section and just keep it squeezed, unstretched in this area, and gradually stretch it as the machine advances. I think there is something missing. I had a nice video after that one. Is it after that? Okay. So it is very important to plan the works in a way that the best possible productivity is achieved. So depending on the number of lines available, we have these three cases. One of them, single line working. So that's just one line. We have to work on that line with a machine. So that means that our excavator has to take the materials from a large distance, and there is a lot of transit movement, which takes a lot of time. That can be helped with placing some of this infill material on the side of the track, so that could speed up the process. I think the best productivity achieved with this single line working was up to 40 yards approximately. The second one, when we have two lines available, we can place a train with the wagons on one, and on the other one, on the line where we install the geocells, we could have either one machine, one excavator taking the material from the wagons, unloading it, and also spreading it, leveling it at the same time, or we can work with two machines, so almost doubling the productivity. We went up to around 70 yards productivity per hour with this case. That's something even better. We have more than two lines. So we place the wagons on the far end, and there is one machine, could be two, unloading the material, and one or two more machines which are leveling the infill on the geocells. Oh, that's the one. So I'll let you watch this one first. So technically, that's the same MFS machine that I showed on the single line working, but on a double line working, this is arguably the most efficient method that has ever been invented, and I think IP Track did that first time. So we work very closely with our counterparts in the United States. They have decades of experience in installing and designing geocells. Mohammed sent them this video, and in half an hour, their director placed it on his LinkedIn account. So even they were impressed by that. You can imagine with that speed, you can install hundreds of meters in an hour. So probably the biggest challenge is connecting the geocell panels. Leveling and compaction. Leveling can be done either with dozers or with the excavator that does the unloading at the same time. And for compaction, we recommend some lighter machines like vibrating plates, because a larger roller compactor could be very heavy, and taking into account that we install geocells on very soft conditions, could create a wave shape on the subgrade. So plates are ideal for compacting the granular infill on the geocell, and that was also confirmed by our colleagues in Germany. Okay, now obviously this is where things could go wrong. We recommend up to 50 millimeters of overfill on top of the geocell before compaction. So technically after compacting, we are coming fairly close to the top of the geocell. Now, obviously, on some sites, we achieved this. That is not because there was a very efficient compaction, it was because there was not enough fill on top of the geocell wall. And that is mainly because the level of the dig and the geocell on top of the dig is not very smooth. So parts of the geocells are sticking out. So when you install your infill, some of them could still stick out, and they can be damaged by the dozer when they do the leveling, or even being collapsed under the compaction tools. Okay, one of the challenges that we have is the interface between two shifts. So technically after the first shift, we have to open the line for traffic and come back next day or next week, depending when the second shift is. And when our dozers start digging out the substrate for the next panel, there is a big risk of damaging the end of the geocell. So we brainstormed this one to death, and we came up with some solutions. Bear in mind, this is just a prototype, so it hasn't been applied on track, but we'll do it at the first opportunity. So this is what we are proposing, to install the first geocell in the first shift, and the last meter from the end of the geocell panel to be kept unextended. So this is technically 1 meter of geocell being squashed. Still in the same shift, we are proposing a short section of sand to be installed, approximately 1 or 2 meters. A little bit of ramp would help, not absolutely necessary. So next time, when we come back in the second shift, this sand can easily be dug out by the bulldozer. This end of the geocell can be marked up on the side of the track so we know exactly where it is. We can stop very close to that one, few centimeters or tens of centimeters with the bulldozer. The rest can be easily removed with shovels. It may take a few more minutes, but that's it. And we can expand that 1 meter of geocell. The reason for this is if we left this one completely expanded, because the last set of cells would have been filled in with sand, you couldn't have connected it easily with the ATRA keys with the next new panel. So now we extend this 1 meter, it's completely empty, and when we install the next panel, it can be very easily connected manually. And the whole process can be repeated in the following shift. So the bottom line of my presentation is, as Sinsin said, gather a lot of data, draw a conclusion, find out what is the root cause, do a good design, as Mohammed said, but all of that can be thrown out of the window if we don't install that product correctly. So we are still learning lots of lessons. We'll put them in the guidance, and that will be available for the whole rail industry. Thank you very much.
Thank you very much. That's the conclusion slide. So moving forward, we're going through with basically creating a guide document, which we're hoping that it will be available online on the PWI website, and it will be subjected to internal and external review. And also we are going through the process of updating the standards with the support from SDE. And and in conclusion, if GSLs offers a great opportunity for building more sustainable railways, and following best practices is key to efficient installation, as Leventi said. And thank you all.